Welcome back. In this lesson, we're going to be covering syllabus point A1.3.5, explain the role of the operating system in managing multitasking and resource allocation. This lesson is only relevant to the higher level students. If you're a standard level student, you should move on to the A2 series of lessons. In the last section, we looked at how we could use polling and interrupt handling to deal with multitasking and how operating systems use scheduling and so on in lessons previous to that. Here we're going to look at the challenges of multitasking and resource allocation, including task scheduling, resource contention, and deadlock. So let's start with the role of the operating system in multitasking. Modern computing systems must handle multiple tasks at once, from user applications to system services, and they're all competing for finite resources like CPU cycles, memory, storage, and input-output devices. The operating system manages this through multitasking, and it allocates resources based on the priority level of different processes. And these resource allocations, these schedulers, need to balance efficiency, fairness, and system stability. Resource allocation and scheduling are essential components for avoiding contention, bottlenecks, and deadlock. And we're going to be covering all of those in this lesson. So let's start with multitasking. Multitasking is the ability of the operating system to execute multiple processes seemingly at the same time or concurrently. And it does that by rapidly switching the CPU between tasks, which is called context switching. Now, context switching is essential for multitasking because every process has its own register values, has its own wait time, has its own priority level, and all of that needs to be saved if you're going to load another process and reloaded when it's that process's turn again. There are different types of multitasking. There is preemptive multitasking, where the operating system decides when to suspend a process to give another process CPU time. And there's cooperative multitasking, where processes voluntarily yield control or give up control back to the operating system. Now, preemptive multitasking prevents any single process from monopolizing the CPU, which is essential to ensure fair distribution. Another task that's needed for multitasking is resource allocation. Now, resource allocation is critical for the operating system to allocate resources. It needs to ensure that active processes can progress without waste, throughput is improved, and conflict is resolved. Key resources include CPU time, memory, storage, input-output of peripheral use. Efficient allocation prevents delays and keeps resource usage balanced. The operating system tracks each running program as a process with its own set of resources, and these include memory, CPU time, open files, and so on. It maintains process tables with information such as the state of the process, is it running, is it waiting to run, has it been blocked by something, its priority, and its resource usage. This is called process management. Now, as the factors change, the OS decides what type of scheduling to use to execute a particular process queue. So when the operating system switches between processes or programs, it saves the state of the current process, all the register values, memories, pointers, and so on in a process table and loads the state of the next process to be scheduled. And this happens extremely fast, often in microseconds, creating the illusion of simultaneous execution. There's nothing simultaneous in a CPU, everything is sequential, but because it does it so quickly, it looks like it is multitasking. Now, for memory management, an operating system uses paging and segmentation as part of the virtual memory system to ensure that each process gets the required amount of memory needs to operate. It often assigns blocks in RAM, possibly extended with virtual memory to processes. The OS also uses device drivers to communicate with specific hardware components and prevents conflicts amongst processes. For example, when you're using the keyboard, there might be four different programs open and they all want access to the keyboard. It manages that. It provides an abstraction layer on top of raw storage hardware like hard drives to enable the file system to operate. And it sets quotas or limits to prevent a single process from using disproportionate resources, ensuring overall system stability. And task scheduling comes into play here. Task scheduling ensures that all running tasks are allocated time on the CPU efficiently. It balances system responsiveness, resource utilization, and fairness amongst tasks. And fairness basically means deciding which process gets the CPU at any given time and involves balancing fairness and efficiency. High priority tasks should not starve, while low priority ones should not monopolize resources. So deciding which processes run next and for how long, that's the job of task scheduling. And it uses algorithms like round robin, priority scheduling, and multi-level queues to help it achieve that. And we've covered all of those before. The next element is resource contention. Resource contention occurs when multiple programs or processes attempt to access the same resource simultaneously, but the resource cannot accommodate multiple concurrent accesses. For example, you've got a memory address and four different programs want to access it. That's not possible. Process can then enter a deadlock state where each process needs a resource held by another, leading to a system standstill. Similarly, live lock can also occur when processes can get stuck in a cycle of constantly requesting and releasing resources, never making any progress. Now, the operating system has a few tools to deal with handling deadlock, and they can use semaphores or queues to coordinate access. And what are semaphores? They're basically synchronization tools used to control access to a shared resource in a concurrent system. So it's an integer variable that can be incremented or decremented atomically. Now you can go and have a look at semaphores in a bit more detail. For example, there are binary semaphores and there are counting semaphores. That's for you to look up in a bit more depth. Locks, on the other hand, are tools used to make sure that only one process can use a shared resource at a time. Queues are pretty easy. They just queue up resource uses by the priority level. The end goal of all of these is to ensure that if two applications, for example, are trying to print to the same printer simultaneously, don't end up causing a deadlock. Now, what is a deadlock? It's a situation where two or more processes are waiting indefinitely for resources held by each other. Now, there are four conditions which can cause deadlock, and these are often named Kaufman conditions. So make sure you know these and you write them down and memorize them. Mutual exclusion, where a resource is only held by one process. Hold and wait, holding one resource while waiting for another. No preemption, resource can't be forcibly taken away from this particular process. And circular wait, processes form a waiting loop. The way to handle these deadlocks, of course, is to prevent these situations from occurring, avoid one of the four conditions, and detection and recovery. Identify and terminate or restart affected processes are great ways to get rid of any particular deadlocks. Now, deadlocks can halt system progress, so prevention is often better than cure. Identifying deadlock situations is critical, and the operating system can employ algorithms to monitor resource dependencies and detect potential deadlocks before they occur. But once a deadlock is detected, the OS must take action to break that particular cycle. This might involve terminating processes or preempting tasks or reallocating resources in the first place. Okay, we're almost at the end of this particular section. On screen, you see a number of key terms related to this section, so do pause the video and make sure you understand them, add them to your glossary before continuing. Hopefully you know enough to answer the following practice questions. What is preemptive multitasking? You should be able to give one example of resource contention. You should be able to name two methods the OS uses to prevent resource contention. You should also be able to explain what are the four Kaufman conditions for deadlock. And you should also be able to explain why context switching is necessary in multitasking. That's all for this particular lesson. If you do have any questions, get back to me in the comments, and I'll see you in the next one.